11 million light years from Earth, there is a galaxy that should not look the way it looks. It is warped, twisted, cut through the middle by a thick, dark band of dust so dense that for decades, telescopes working in visible light simply could not see what was happening behind it. Astronomers have known about this galaxy for a very long time, longer than most of the objects that make headlines in modern astronomy. It is one of the brightest objects in the entire radio sky, visible even to backyard telescopes on a clear night. But what was actually happening at its center, what was actually causing its strange, mangled shape, remained frustratingly out of reach, hidden behind a wall of dust that no previous instrument had the combination of power and precision needed to see through. This month, to mark 4 full years since its very first images stunned the world, the James Webb Space Telescope turned its full attention back to that galaxy. And what came back is being called some of the most detailed, most revealing images the telescope has ever produced. The galaxy is called Centaurus A, and the story of what actually happened to it and what Webb just revealed hiding behind its dust is one of the clearest windows we have ever had into how galaxies and the supermassive black holes buried at their centers actually grow up together over billions of years. First, the anniversary itself, because the timing here is not a coincidence. On July 12, 2022, NASA released the first full-color science images ever captured by the James Webb Space Telescope, a moment that instantly redefined what astronomers thought was possible in observational astronomy. That telescope, a joint project of NASA, the European Space Agency, and the Canadian Space Agency, carries a primary mirror more than 21 feet across, built from 18 hexagonal gold-coated segments, folded up to fit inside a rocket, and unfolded piece by piece in space after launch, a deployment sequence so complex that engineers described it, at the time, as having hundreds of single points of failure, any one of which could have ended the mission before it ever returned a single image. It orbits not the Earth directly, but a gravitationally stable point roughly 1 million miles away called the second Lagrange point, trailing behind our planet. Shielded from the sun's heat by a tennis court-sized sunshield that keeps its instruments cold enough to detect the faint infrared glow of the earliest, most distant galaxies in the universe. Unlike Hubble, built primarily to see the universe in visible light, Webb was designed from the ground up to observe almost entirely in infrared, precisely because infrared light can travel through clouds of dust and gas that block visible light entirely, and because the light from the very earliest galaxies in the universe has been stretched by the universe's own expansion into infrared wavelengths by the time it finally reaches us. 4 years later, in July of this year, the telescope has continued operating at a level NASA itself describes as better than anticipated, still returning science data with no significant loss of performance, still expanding what we understand about the universe with results that its own engineering team did not fully expect this early into the mission. To mark that 4th anniversary, rather than pointing at something entirely new, astronomers chose to send Webb back to a galaxy that had already been photographed and studied for decades, specifically because they knew Webb's particular combination of infrared instruments could reveal something about it that no other telescope at any point in the history of astronomy had ever actually been able to see. Centaurus A, also known by its catalog designation NGC 5128, sits close enough to Earth, in cosmic terms, that it has been a favorite target of astronomers for generations. Centaurus A, also known by its catalog designation NGC 5128, sits close enough to Earth, in cosmic terms, that it has been a favorite target of astronomers for generations. Its unusual appearance was first catalogued in visible light in the 19th century, but its true significance did not become clear until the birth of radio astronomy in the 20th. In 1949, using some of the earliest radio telescopes ever built, Australian astronomer John Bolton and his colleagues identified Centaurus A as one of the very first extragalactic radio sources ever discovered, a galaxy blasting out radio emission powerful enough to be picked up by instruments still in their infancy. That discovery helped launch an entire new branch of astronomy built around studying galaxies not just by the visible light they emit, but by the radio waves, infrared light, and other invisible radiation pouring out of their most violent regions. Decades later, Centaurus A remains one of the brightest radio sources in the entire sky, visible even to backyard telescopes on a clear night as a strange, mottled smudge, its true structure obscured behind the same dust lane that would eventually become the primary target of Webb's anniversary observations. But close does not mean simple. Unlike most nearby galaxies, which tend to settle into calm, predictable shapes over time, Centaurus A is a mess, and that mess has a specific, violent origin. Roughly 2 billion years ago, long before anything resembling complex life existed on Earth, Centaurus A collided with another, smaller galaxy. That collision did not simply distort its shape, though it certainly did that too, twisting what was likely once a fairly ordinary elliptical galaxy into the warped, irregular structure astronomers still see today. It also flooded the galaxy with an enormous supply of fresh gas and dust. The raw material stars are built from triggering waves of intense new star formation that are, remarkably, still ongoing right now, 2 billion years later. And that same gas and dust did something else. It fed the supermassive black hole sitting at the very center of the galaxy, an object with a mass far exceeding our own sun, giving it an abundant supply of material to consume and turning what might otherwise have been a quiet, dormant galactic center into what astronomers call an active galactic nucleus, a violently energetic core where the black hole is actively pulling in surrounding matter and blasting a portion of it back out in the form of powerful jets of superheated plasma, traveling at extraordinary speeds far beyond the visible edges of the galaxy itself. Those jets are a large part of why Centaurus A became famous as a radio source in the first place, extending outward across distances vastly larger than the visible galaxy they originate from, glowing brightly at radio wavelengths as the high-speed particles within them interact with surrounding magnetic fields. Very little of the material a black hole pulls toward it actually falls in directly. Some portion instead gets funneled along magnetic field lines and blasted back outward in these narrow, focused jets, a way for the black hole to release enormous amounts of energy back into the galaxy around it, even while it continues feeding on the matter closer to its center. That combination, an ancient merger, ongoing star formation, and an actively feeding supermassive black hole all happening simultaneously in a galaxy close enough for us to actually study it in detail, is what makes Centaurus A one of the single most valuable laboratories in astronomy for understanding how galaxies and the black holes at their centers grow and change together. The problem, for decades, was that the very same thick lane of dust responsible for hiding the galaxy's most interesting activity also made it extremely difficult to actually study. The Hubble Space Telescope, operating primarily in visible light, could photograph Centaurus A in exquisite detail, capturing the sharp outline of its warped dust lane silhouetted against the galaxy's glowing stellar body, an image that has become one of the most recognizable in modern astronomy. But sharp outline is not the same as clear view, and Hubble simply could not see through that central dust lane the same way headlights struggle to cut through thick fog rather than actually piercing it. NASA's Spitzer Space Telescope, an earlier infrared observatory that operated for more than 16 years before being retired, could trace the warm dust in Centaurus A on a broader scale, giving astronomers a general sense that something significant was happening in the galaxy's core, a rough map of where the heat and activity were concentrated. But Spitzer's resolution was not sharp enough to pick apart the fine detail of exactly what that activity actually looked like, star by star, structure by structure, leaving a frustrating gap between Hubble's crisp but dust-blocked visible light view and Spitzer's dust-penetrating but blurry infrared one. Ground-based observatories added their own piece to the picture as well. Astronomers released a side-by-side comparison alongside Webb's new anniversary images, pairing a ground-based view of Centaurus A captured by the European Southern Observatory with Webb's own infrared observations. The contrast makes the scale of the improvement immediately obvious even to a casual observer. Where the ground-based image shows a hazy, softened silhouette, its detail smeared by the light-scattering effects of Earth's own atmosphere in addition to the galaxy's dust, Webb's version resolves individual structures within that same dust lane with a sharpness no observatory sitting underneath our planet's atmosphere could ever fully match, regardless of how large its mirror happens to be. That is precisely the gap the James Webb Space Telescope was built to close, and its new anniversary observations of Centaurus A, released on July the 6th and 8th of this year, close it about as dramatically as any single set of images could. Using its near-infrared camera, known as NIRCam, combined with its mid-infrared instrument known as MIRI, Webb captured Centaurus A across a range of infrared wavelengths sensitive enough to cut straight through the dust that had frustrated Hubble for decades, while still retaining sharp enough resolution to resolve individual stars packed densely throughout the galaxy's structure. Where previous images showed a smudged, obscured band of darkness running through the galaxy's center, Webb's new images reveal a densely packed tapestry of individual stars sitting directly behind it, an entire galactic population that had simply been invisible to every telescope that came before. The MIRI data in particular exposed activity around the galaxy's central black hole that no previous observation had captured with this level of clarity. Webb detected fast-moving ionized gas being physically pushed outward by the black hole's own activity, direct visual evidence of the central engine reshaping the material around it in real time, rather than simply inferred from indirect measurements. The data also revealed a warped, rotating disk of warmer molecular hydrogen gas sitting close to the galaxy's core, twisted out of a simple flat shape, almost certainly a lingering structural scar from the ancient galactic collision that shaped this entire system in the first place, still visibly distorting the gas dynamics near the black hole 2 billion years after the actual impact occurred. And then there's the detail nobody can yet fully explain. Tucked into the MyRI image, alongside the glowing stellar nurseries where new stars are actively being born and where those young stars in turn seed their surroundings with fresh gas and dust, sits a distinct, curious S-shaped structure, visible clearly enough in the data to be unmistakable, but strange enough in its shape that astronomers studying the images are not yet certain how it actually formed. One live possibility under discussion is that the galaxy's active black hole played some role in carving it out, its jets or its outflowing material bending and shaping the surrounding gas into that unusual curve. But as of right now, that connection remains an open question rather than a confirmed explanation. Other galaxies do show similar looping or spiral-shaped gas structures near their centers, sometimes tied to the gravitational influence of a bar-shaped inner structure, funneling gas inward, sometimes tied to the leftover motion of an old merger still slowly settling into a more stable shape, and sometimes tied to feedback from the central black hole itself pushing gas outward in an asymmetric pattern rather than a simple, even sphere. Which of those explanations, if any, actually applies to Centaurus A's newly revealed S-shape is exactly the kind of question follow-up observations and more detailed modeling will need to sort out. One more small mystery embedded inside a much larger picture that Webb has just made visible for the first time. This is not simply a case of a familiar galaxy looking prettier in a new photograph either, however striking the images themselves are. The results are being considered alongside a set of research findings tied directly to the same anniversary release, including work published in Astronomy and Astrophysics, and additional analysis shared as a preprint the same week as the new images, together providing one of the clearest pictures astronomers have ever assembled of exactly how an ancient galactic merger continues to actively shape both star formation and black hole behavior, billions of years after the actual collision took place. That is the real significance sitting underneath the anniversary framing. Centaurus A is not just a pretty target chosen because it photographs well. It is direct, ongoing evidence that a single cosmic collision 2 billion years in the past is still actively driving measurable physical processes today, still funneling gas toward newly forming stars, still feeding a hungry black hole, still bending gas dynamics near the galactic center into shapes scientists are only now able to actually see and start to explain. Step back for a moment and consider what it means that a telescope 4 years into its mission is still capable of returning results this significant from a galaxy that has already been studied for generations. Centaurus A was not some newly discovered object waiting to be found. It has been photographed, cataloged, and analyzed by multiple generations of astronomers using multiple generations of telescopes, going back decades before Webb ever launched. And yet, pointing an instrument sensitive enough at exactly the right combination of infrared wavelengths was enough to reveal an entire hidden population of stars, direct evidence of a black hole actively reshaping the gas around it, and at least one genuinely unexplained structure sitting in plain sight, all inside a galaxy astronomers thought they already understood reasonably well. That is, in many ways, the real story of Webb's first 4 years, not simply finding new, previously unknown objects at the very edge of the observable universe, remarkable as those discoveries have been, but returning to familiar, well-studied targets close to home, and discovering that there was still an enormous amount hiding in plain sight, simply waiting for an instrument capable enough to actually look. There's also something worth sitting with in the choice of anniversary target itself. NASA could have marked this milestone with an entirely new discovery, a fresh, previously unseen object plucked from the deepest, most distant reaches of the universe, the kind of image built specifically to generate a single dramatic headline. Instead, the choice to return to Centaurus A, a galaxy already familiar to generations of astronomers, and to reveal an entirely new layer of detail hiding behind its dust, makes a quieter, but arguably more important point about how this telescope is actually being used. 4 years in, Webb is not simply chasing the newest, most distant record to break. It is being turned back towards some of the sky's most well-known objects, and consistently finding that our previous picture of them was radically incomplete, a pattern that has repeated itself across nebulae, star clusters, and now, in dramatic fashion, an entire actively merging galaxy sitting relatively close to our own cosmic backyard. 4 years after its very first images changed how astronomers see the universe, the James Webb Space Telescope is still finding entirely new layers of detail hiding inside objects we thought we already understood, still operating better than engineers originally expected, and still 4 full years in, delivering the kind of images that make astronomers stop and admit they are looking at something genuinely new, even in a galaxy they have been studying for generations. It is worth remembering just how uncertain this entire mission once looked before it ever reached this point. Webb spent more than 2 decades in development, facing repeated delays and cost overruns, significant enough that its cancellation was seriously debated in Congress more than once before it ever launched. When it finally lifted off on Christmas morning in 2021, it then had to survive a month-long journey to its final orbital position, unfolding its sunshield and its segmented mirror in a sequence of maneuvers that had never been rehearsed in full on the actual flight hardware, because there was no way to test the entire deployment process on Earth under true spaceflight conditions. Every one of those steps had to work correctly, in the correct order, with no possibility of a repair mission if something went wrong, because Webb's final orbit sits roughly 4 times farther from Earth than the Moon, well beyond the reach of any spacecraft currently capable of reaching it. That it succeeded at all was, by the admission of the engineers who built it, closer to a best-case outcome than a guaranteed one. That it has now spent 4 full years returning science data at a level exceeding even those optimistic early expectations is the quieter, less flashy half of this anniversary story, the part that makes images like these new views of Centaurus A possible in the first place. There's a particular kind of satisfaction for the scientists who spent decades building this telescope and watching it return to a galaxy that has already been studied by generations of their predecessors, and find something genuinely new sitting there anyway. Centaurus A was not waiting to be discovered. It has been photographed and cataloged since the 19th century, studied as a radio source since the 1940s, imaged in stunning detail by Hubble, and mapped in broad infrared strokes by Spitzer decades before Webb ever existed as more than a proposal on paper. And yet all of that accumulated history did not prevent Webb from finding an entire hidden population of stars, from watching a black hole visibly reshape the gas around it in real time, and from uncovering a structure so unusual that nobody currently studying the data can fully explain how it got there. That is not a story about one telescope replacing the ones that came before it. It is a story about how much can still be hiding in the objects we think we already know best, waiting for exactly the right combination of wavelength, resolution, and sensitivity to finally bring it into view. If this is the kind of story you want more of, subscribe, and let me know in the comments which of Webb's images from the last 4 years has stuck with you the most.